Hey everyone, we are the water team and today we will be presenting our MAE 162E final project on the sensor boat. So our team members include Savya, Sydney, Rebecca, Hubert, Jonathan, Felipe, and Haokun. So in the beginning of our Capstone project, we identified a problem that we wanted to solve. And so what we wanted to solve was the issue of maintenance of fish farms in terms of water quality. So some of these causes of unclean living environments for fish can include improper cleaning or regulatory methods, poor chemical or nutrient composition, and insufficient use of equipments like filters. So then we narrowed our scope through research using questionnaire, observation, and documentation methods. And so what we settled on was a proposed technical solution, which was to create an automated monitoring system. And this comes in a form of a sensor boat, which will take readings at specific depths, then relay this information to the user. So we have four objectives for this project. First, we want it to be reliable, so it is able to withstand certain impacts and weather conditions. Next, we also want it to be autonomous, which is to be achieved with the pathing and docking system. We also want high accuracy data collection, so we implemented a Wi-Fi communication system. And lastly, we want convenience, meaning translating the data in a user-friendly way so that it is accessible to, say, an everyday employee at a fish farm. So the sensor boat works by driving around pools on a pre-planned path created using MATLAB and the pool's geometry. This device monitors pH, oxygen content, and the temperature of the pool by lowering sensors into the water and collecting corresponding data at different depths and location. So we believe that this product will be most beneficial to use in fish farms and large-scale aquariums to ensure healthy living conditions for the animals. So the sensor boat consists of three subsystems. The first is the structural design subsystem, which consists of the boat body, the housing units for the electronics, and the base station. The second subsystem consists of the electronic and software components of the boat. And lastly, the third subsystem includes the simulation and subsequent analysis for the boat's software, structure, and movement. Next, Haokun will begin walking us through the boat's structural design.
For the boat structure, we choose to use catamaran. Catamaran is the multi-hulled watercraft, featuring two parallel hulls of equal size. It is a geometry-stabilized craft. Unlike the monohull, the stability of the catamaran is derived from its wide beam, rather than a plastic keel. Catamaran has several advantages. It has more stable geometry, less hull volume, smaller displacement, and shallower draught than the monohulls of comparable length. The catamaran has smaller hydrodynamic resistance. The wider stance of catamarans reduce both heeling and water-induced motion. A catamaran will also resist the overturning moment of the sail by its beam alone without having fat hulls for from stability or a lead ballastic. Therefore, the catamaran do not need to consider the positional relationship between the center of gravity and the center of buoyancy. In order to adapt to different aquariums, our boat cannot be too large or too small. After several adjustments, our boat have 44 cm length, 30 cm width, 20 cm high. When we take a closer look, there is a hole in the middle of the boat. A spool will be placed there and respond to drop down the sensor box. Because of the catamaran structure, the hole will be above the water line such that water will not enter the boat. Around the hole, there are two thin walls to create a chamber, which will separate the wet spot from the electronic component.
So in particular, the spool will be powered by a brush motor with a 63:1 gear ratio, and it will also be outfitted with a slip ring to prevent tingling and stress on the cables.
Instead of two main hulls, the propeller will be held in a small hull produced from the bottom. Placing the propeller in an axial hull will avoid damaging the balance of two main hulls, and a separate hull will reduce the risk of propeller leakage. Two U-shaped chimneys are placed at the rear of the boat, which can keep the good air circulation in the boat. Air circulation can avoid the danger caused by heating of electron components. The U-shaped design can prevent water from entering. We choose polypropylene as the bowl's material. It is widely used in manufacturing of small bowls. Polypropylene has excellent water resistance, and it is extremely impact resistant. The density and the cost are lower than other material. Therefore, it is the perfect material for our bowl. Then, I did some impact studies for the bowl. In this slide, they are the result when the bowl against the wall. On the right-hand side, the picture shows the stress distribution of the bowl when the front of the bowl hit the wall, with its maximum velocity, which is 1 meter per second. On the left-hand side, the picture shows the stress distribution of the bowl when the side of the bowl hit the wall caused by large wind or wave with 1 meter per second. Both of the study results show that the bowl structure will not fail under those situations. This slide is the result when the bowl is dropped down from 1 feet high. On the left-hand side is the stress distribution when the bowl was dropped parallel to the ground. On the right-hand side is the stress distribution when the bowl was dropped with an angle, such that all the impact is concentrated in one point, even though the maximum stress did not pass the tensile strength. The impact studies shows that the bowl structure has no problem in general operation.
I will now be discussing the design for the sensors and their associated electronic components. Provided here is an overview of the electronics locations within the boat. On board, we'll be using 2 Arduinos, 4 waterproof ultrasonic sensors, and an electronics box housing the converter boards for the sensors. The sensor bodies and probes will then be housed in the sensor box, which is submerged into the water on a reel system. We use the following sensors to model the design and dimensions for the sensor and electronics encasements. Their pictures and part numbers are displayed here. All the sensors are submersible and come with individual converter boards, making them all Arduino compatible. The left-hand picture is a PNP sensor box developed by RAK Accessory and is submersible in up to 1 meter of water. This product informed my own design for the sensor box. Thus, each of the hole cutouts along the bottom-facing edge of the box are surrounded by a rubber ring to provide a seal and prevent water infiltration. The sensor cables then exit the box through a hole on the top sealed by a PG9 cable gland. Finally, the box lid is screwed to the top, and a rectangular cutout along the top face of the box aligns with extrusions on the lid to create yet another seal. All the sensors and cables are submersible, so water infiltration may not pose a major threat. However, keeping these sensors in a dry environment will decrease the risk of wear and tear and increase the accuracy of the data. The sensor box is then attached to the boat's reel with a mechanical cable capable of lowering the box by up to 1 meter deep. The mechanical cable will bear the weight of the sensor box to decrease strain on the sensor cables. The sensor cables themselves are also wrapped around the reel but hang freely in the water. Coming off the reel, the sensor cables are then attached to the electronics box located on the hull of the boat. The pH and oxygen sensor cables are attached to their converter boards via a BNC connection. The distance sensor cable is attached to its converter board with a USB Type B, and finally the temperature sensor connects to a 3-pin connector. The converter boards are then routed via ribbon cables to a central PCB within the electronics box. This PCB is routed to the Arduino using a 20-gauge 8-conductor cable. This is shown as the large green cable in the CAD model. This cable provides power to the sensors and returns data to the Arduino and Wi-Fi systems. Savya will discuss the store and transfer of data later in this presentation. Here is a closer look at the wiring scheme for the sensor and electronics box connections. This wiring diagram was designed with Visio and was mainly used to plot the paths of sensor data and to make sure there were enough connection points on a single Arduino to support a 4-sensor design. As I said before, we are using 2 Arduino systems in the boat. Arduino System 1 includes the sensor connections I went over and the motor and motor driver used to operate the reel. The second Arduino system includes the onboard distance sensor, the motor and driver for the boat propeller, and the servo motor used to turn the rudder. The motors and driving mechanisms will be discussed further in the presentation. Finally, here is the overall wiring schematic for both Arduino systems. I was able to model these connections much more broadly using the SOLIDWORKS routing tool. The wires in the CAD show each component's connection to their sensor cables and their designated Arduino to route to. I did not show each individual pin connection as I use this tool as more of a general display and to confirm that there was enough space in the boat for all the connectors and cables. Many of these cables overshoot their diameters as well because they can be replaced with much smaller and more manageable ribbon cables. Savya will now discuss the software and data transfer for the system.
The system would be deployed in a large pool of water, eliminating the possibility for the user to physically and manually control the boat. For the large part, it would be the most convenient and apt to have a remote control system for the boat, for the user to command the boat and the sensors and to relay the data collected. The simplest and most powerful tool for this purpose is a personal computer for an end user with very less technical knowledge. The computer allows us to leverage MATLAB and its robust data visualization and Arduino tools for our purpose. Often, radio and Bluetooth networks are marred with the problems of insufficient range and interference and do not offer as robust a gateway for communication as Wi-Fi. Using Wi-Fi as our channel of communication allows a user to communicate with the boat over an existing Wi-Fi network, which is a pretty common thing in aquariums. The ESP8266 module for Arduino helps facilitate this. The computer screen would be the interface from where the user would communicate with the boat. For it to be easy to use, it is essential that the system have a good graphical user interface, which is robust both on the front end and the back end side. The front end is the user-facing side of the system, and the back end is the code that runs in the background. Breakdown of any of these two systems could cause unnecessary frustration for the user. The ESP8266 collects data and sends data to and from the Arduino to the serial port on the computer, from where the data is picked up by a MATLAB script and displayed on a dashboard for the user. The user can then click the appropriate button and either command the boat or view its data as plots. The data is collected and stored in a table on the computer. Storing it in a table helps in data visualization and data correlation. Data visualization is segmented into two formats: plain text and heat maps or color maps. Heat maps or color maps show spatial distribution and concentration of O2, temperature, and pH. The plain text display shows the distance of the pool edges from the boat, the depth of the sensor box below the surface, and a visual of the boat's path in the pool. The user can control the propulsion, boat power that is on or off, and lower or raise the sensor box using the spool command. Here is a sample of how the graphical user interface would look. On the top left, you can see a color map of the concentration of O2 in the pool. The pool is a rectangularly shaped pool, and oxygen is distributed according to the colors shown, with blue being the least concentration and yellow being the most concentration. To the right, you can see the distance of the boat from the 4 pool edges.
So we utilized Tinkercad to simulate the electrical functionality of the sensor system. We did this by assigning data points for oxygen, temperature, pH, and distance, collected it and displayed it on the GUI. This was first done on the Arduino software, then converted to MATLAB for more convenient processing.
The motivation behind the system is to allow the boat to follow a specified path given by the user and to allow the boat to decide its own path around the pole with some algorithm without any user inputs. The propeller and rudder will be used to drive the boat, therefore a controller for the rudder and the propeller are needed to meet pathing specifications. Without them, any disturbance would affect the pathing of the boat, leading to undesirable results. The goal of these two controllers will be to tell the boat how much the rudder should be turned and how much RPM should be given to the propeller to achieve a specific location or path. This process will also allow for the correct choice of the propeller, rudder, and motors necessary for motion. This could be achieved by running simulations on Simscape or drawing free-body diagrams and manually creating a Simulink model. The Simulink approach was chosen for this project due to difficulties with using Simscape to model viscous effects. Since the dynamics of the boat are affected by water conditions, CFD simulations have to be done to create the control systems. The viscous forces on the boat determine how fast and far it will move and how much it will turn based on a specific angle, so 3 simulations are needed. One for the propeller, another for the boat, and another one for the rudder. The simulations done on the boat will be done at various velocities to determine top speed of the boat. Simulations of the propeller will be done at several velocities to find how much torque is needed to drive the motor and how much thrust can be provided by it. Simulations on the rudder will be done at various velocities and angles of attack to determine how fast the boat could turn and how much torque could be provided at a given speed. Since the geometry of the boat is already fixed, only the propeller, motors, and rudder have to be chosen to achieve the desired dynamics. The following procedure was used to choose them. First, we have to choose the propeller and run a simulation to see if the boat can achieve the desired speed. Then we have to select a motor that can run at the required torque. After that, we can design the rudder and run simulations to see if the torque generated is good enough. And then after that, we can design both controllers to see if they meet the specifications. And if the design doesn't work, then we have to iterate the whole process as shown in the figure. Requirements for the rudder included being symmetric, being able to track input at fast rise time and no error regardless of disturbance. Possible choices could be the NACA 0012 or NACA 0024, for example. Requirements for the propeller and motor would be that they must allow the boat to drive up to 2 meters per second, even though it will probably move at a much slower velocity. The boat must also be stable and track input at very windy conditions, and the motor must run close to the nominal torque. Possible changes could include changing the size of the propeller geometry and varying the gearbox and power of the motor. This is one example for the simulations run of the boat assembly. As you can see, it only includes the bottom half of the boat that is submerged underwater with varying velocities. The force on the opposite direction of the flow was the main result for the simulation. The figure shows a simulation example run of the rudder. It contains varying angles of attack and wind velocities. This is another example of the simulation for the propeller and motor. RPM of the propeller was changed in the simulation, and the torque required to turn the propeller and thrust generated by it were obtained. These are the results taken from the simulations done on the rudder for 1 meter per second velocity and varying angle of attack. The lift coefficient plot was used to see if the simulation's results were good enough compared to NACA data. The lift plot was used in a block diagram on the controller and will be shown later. These are the results taken from another simulation from the rudder to determine the normal force on the rudder. The graph was linearized and was later used to build the block diagram for the rudder controller. These are the results for the boat, propeller, and motor simulations. The MATLAB graphs on the bottom are taken from the manufacturer and were used to select the motor. The simulation data was used to modify the propeller and was used in the propeller block diagram, which will be shown later. After doing the simulations, the final components chosen were the NACA 0012 airfoil with 1.77-inch chord length, a propeller with 68 mm overall diameter, and a Pololu DC motor with 63:1 gearbox. If the Simulink simulation shows good results, then these components are good enough. After getting all the necessary data from the simulations, the dynamics of the boat can be found with free body diagrams.
The slide shows the process of obtaining the governing equation for the turning of the boat and controlling of the rudder. The boat was moved from its current After getting all the necessary data from the simulations, the dynamics of the boat can be found with free body diagrams. The slide shows the process of obtaining the governing equation for the turning of the boat and controlling of the rudder. The boat was moved from its current location to another, which is either specified by the user or by the algorithm. The difference between the theta b and theta g angles in the figure are the reference command for the controller. The block diagram is shown here with the plots mentioned earlier from the rudder simulations. The reference command is the difference between the current and desired boat angles. The input is the angle of the rudder, which can be controlled with servo.right, for example. MD is a disturbance torque, and if results from the Simulink prove undesirable, the rudder could be modified to obtain different values for A and B, as can be seen from the diagram. A PD controller was designed as shown in the slide. This was done to have a general idea of where the poles and zeros could be placed to achieve a small overshoot and rise time. A PID was then designed using the root locus method to change the gain, poles, and zeros locations. This was done to eliminate error due to disturbances. This was how the block diagram was recreated on Simulink. It follows the same idea as last slides, but with a saturation block after the input. This block allows us to limit how much input can be provided by the motor. After running the simulations, it was found that the motor could not surpass plus or minus 600 RPM under given conditions, or this would surpass the torque recommended by the manufacturers to run it constantly. However, controllers in real life are not continuous since they have a certain sampling rate. Although not shown here, another Simulink diagram was created to see how discretizing the controller would affect the response. It's basically the same, but with a sampling and zero order holding blocks. The sampling rate was of 9,615 Hz, which is the sampling rate of the Arduino Uno. The figure shows the response for SAP reference input and no disturbance for continuous and discrete time controllers. This is another example of the response for 180-degree reference input and 1 kg force at the edge of the boat. This is another example of the response for 180-degree reference input and 5 kg force at the edge of the boat. With the exception of this example, the other cases showed to be stable with fast enough rise time and no error. It is unlikely that 50 kg force at the edge of the boat will ever occur in this situation, so this design was used for the boat. The same procedure was done to the propeller controller. The graph was taken from the propeller simulations. You can be seen that the plan is not linear, so they had to be linearized in order to fit the block diagram. The same method as mentioned earlier was used to design the 3-time PID controller for the propeller. This is the continuous time controller Simulink block diagram for the propeller. The figure shows an example for the response with 1 cm input and no disturbance. These are the responses obtained for 400 meter reference input and step disturbance. Both look very stable with no overshoot and are acceptable for the design. Responses could be further optimized by getting a faster controller, designing the controller with a direct approach, or using a state space method.
The base station essentially contains 4 components: induction charger, radio transmitter, linear actuator, and the power cord that connects all those 3 main components. The function of the base station itself is first, for charging the boat. Second, housing appliances that cannot be put inside the boat. For example, there might be potentially a need that requires a higher power CPU to process a larger amount of data, and that CPU might be too big to put into the boat, and that would be placed in the base station. Thirdly, base station works as a place to hold the radio transmitter to send signal to the boat, to locate it, and send information. And lastly, the base station is the reference point in respect to the boat that allows it to map the boundary and locate its coordinates. There should be two linear actuators attached to the base station with brackets, which work as a gate to hold the bolt inside. One on the front, one at the back, as the back has a larger entrance to allow the bolt to enter. The stroke of the linear actuator would be 200 millimeters, and the stroke on the front would be 100 millimeters. The gear ratio of the linear actuator is 22:1, which gives us a speed of 48 millimeters per second of the stroke coming in or going out. The linear actuator works on a simple switch which can be activated remotely from the Arduino through radio. It is also a splash-proof. For the induction charger, it is screwed onto the side of the metal bar of the base station. It works as a pair with the coils inside the side of the bolt. The maximum distance for charging is 4 centimeters, which is sufficient because the maximum gap, assuming the bolt is to the furthest to the left, is less than 2 centimeters. All induction chargers in the industry run with the same QI standard, so the design and configurations are interchangeable with other manufacturers, regardless of the size. The power output of this particular charger that we picked is 10 watts. For the radio transmitter/receiver, it works as a pair from the bolt to the base station. The picture on the left is the transmitter, while the picture on the right is the receiver. The transmitter runs on 3 volt to 12 volt, and the frequency that it communicates with the 5 volt receiver is 315 MHz, so it is very unlikely to receive a significant interference because in the US, broadcasting operating in a frequency of around 100 MHz. The maximum working distance for this radio transmitter is 200 meters. By placing 3 transmitters around the pool, constantly sending signal to the receiver, and configuring the time it takes to receive a signal on the boat from the base station when it is at rest. Once the boat starts moving, the change in the time it takes to transmit those signals would be accounted as the difference in the distance it moved, triangulating a new coordinate for the boat working as a local GPS. So, for the pathing of the boat, if we assume that we don't know the layout of the area, there's a need to map out the boundary of the pool before executing the pathing function. As such, we ran a simulation in MATLAB to show how it would work. For mapping the boundary, on the right, there's a sample map predetermining the boundary as the black area on the map. Assuming that the boat goes from the top left to the bottom right, the boat side and front faces the direction of the boundary. We'll record that location and create a pose. This picture on the right is a graph showing the poses recorded. However, the actual scenario would be slightly different because it works with the 4 ultrasonic sensors on our boat. Because the boundary is not known, the poses recorded from the sensor is with respect to the location of the boat, and because the sensor has a 4 meters limit, the boat should first go around the boundary of the pool and map out the area before proceeding to the grid pathing. Originally, we thought that we should use the robotic toolbox to keep the boat constantly parallel to the boundary while mapping the boundary. But when we did it, it doesn't do so well with sharp corners, and when it's always parallel, the data points from the back sensor will be very limited as the mapping poses would only rely on the side sensors and the front, possibly creating a significant error when mapping the boundary. So, we ultimately decided on this solution, as you can see on the graph. The boat pathing for the first loop is moving in a sinusoidal wave based on the boundary. The logic behind this is by using the sensor data for the side. If it is too close to the limit, it will turn away from the boundary, and if it is too far, it will turn the other way to get closer to the side, creating this waveform pathing while allowing the front side back sensors to record the distance of the boundary with respect to the sensor itself, mapping the known poses so that we can map out the area. Once the loop is over, after mapping out the boundary, we can then use those boundaries to create grids on the map. Those grid points will be used in navigation for the boat so that it can reach the whole map efficiently, providing sufficient data points for the other sensors, such as the oxygen sensor and the temperature sensor. On the side, this is a video showing how the boat would proceed under the grid pathing program. So the boat will start from the bottom center position, go to the furthest grid on the bottom right corner, and then move along the corners in a counterclockwise motion. And also, this video was sped up 8 times and the boat speed was actually scaled up to 20 times. So it looks fast, but in actuality, it's moving in reality an actual speed that is 1 meters per second and turning in 1 degree per second. After the first round in the grid pathing, the next grid would be similar to the first, except that it would reduce its scale by 1 grid on both directions. And when the grid cannot be reduced any longer, meaning that it has reached the center area, it will return to the base station. This graph is a representation on the path taken by the grid pathing function. There is also a chance that the map itself will have obstacles. The boat program from the robotic toolbox allows the boat itself to go around the obstacles when there's an interference, like how it is shown in this graph. The red area are obstacles, and the green area is the path that the bug program provided, so that the boat can follow this path to go around the obstacles to reach its destination. According to the path simulation and control simulation, here is a motion analysis animation to show that how a boat would work. The sensor box would be dropped at certain locations to obtain data at a lower water level. Here it's in the sequence of going back to the base station, it's turning. And once it's inside the base station, the gate will close to hold the boat in place. And for the concluding summary, for our boat, we decided that the boat shape would be a catamaran shape. For manufacturing option, for the boat body itself, we would use the mold injection. And as for the base station, we would use 3D printing. According to our impact studies, we show that our boat is impact-proof, waterproof, and wave-proof. And as for our data, it would be collected over Wi-Fi and relayed to a computer that would serve as a control hub so that the user can control it without actually having to physically stay next to the pool. And we would use the radio transmitter and receiver to work as a local GPS and the sensors in mapping out the boundaries so that it could proceed to the grid pathing. And this is a general budget for our boat, and the total came out to be around $883. And this is our presentation. Thank you.